recording. So two things. So there were two methods of integrating. One was using, just the method of indefinite integrals. And the second was using the path. And we use this often, and we discussed two important examples for integration by path. Integral of 1 over z dz over a circular path C, unit circle, with center at O. So we know that function is not analytic at z equal to 0. So because function is not defined. And if we circulate along that path, then we get 2 pi I. Otherwise, if there is no, if the function is analytic throughout and we take a circular path, you get the integral as 0. So that's what we showed by this example, f of z equal to z minus z naught whole power m. So yeah, so we got this. So if m not equal to -1, we get 0. But if m equal to -1, that is this integral, again we get 2 pi I. So these were the two very important integrals. Okay. Now, just a second. So now we'll build a platform for Cauchy's integral theorem. Now, before we start Cauchy's integral theorem, we have to have some prerequisite definitions. First one is of what is a simple closed path. So let's take examples. We know circle, of course. We have rectangle or a square. Then we can have of any arbitrary shape. Okay. Now these are all simple closed paths of any shape, but they do not intersect or touch themselves. Okay. So simple closed path are closed paths that does not intersect or touch or touch itself. This is simple closed path. Closed paths that are not simple, we can take other examples. So this is also a closed path. This is a closed path. This is a closed path intersecting each other. These are all closed paths. So these are closed paths that are not simple. Okay. Next. So that's a basic definition of a simple closed path. Next, we have the definition of a simply connected domain. Say D. So a simply connected domain. So the definition is it is a domain in a complex plane such that every simple closed path in D enclose only points of D. That means if I take a simply connected domain, that means any closed path I take, all the points of that path are subsets of D, and the points within the closed path are also subsets of D. So they are examples of, these are whatever we discussed earlier are the examples of simply connected domain, like a circle, a rectangle, a disc like this, a mushroom shaped closed path like this, anything. Now, the important point to notice, there are no gaps or holes or breaks in the domain. What we say continuous in real functions is connected in complex functions, in complex plane. Okay. Now, a domain which is not simply connected is called as multiply connected domain. This is a domain which is not simply connected. So let's see examples of this. This is an example of a doubly connected domain. Okay. So points here, they do not belong to D in this whole segment. All other points belong to D here. These all belongs to D. This is D, this is D. That which is marked with cross does not belong to D. So we can think further examples. Now, this has how many boundaries? Two boundaries. One, two. One closed path as a boundary, another closed path as a boundary. Same here. So these two are called as doubly connected domain. You require two paths for boundaries. This is a triply connected domain. And this is quadruply connected domain. Okay, these will be very crucial in our definitions of Cauchy's integral theorem. Okay. So these are the basics of what is a closed path, a simple closed path. And then what is a simply connected domain? It should be a simple closed path, very important, and without any gaps and breaks. And if there are any gaps, even one point which does not belong to D, then there is a boundary surrounding that point. So it will be a doubly connected domain, even if one point is not belongs to D. Okay. So now comes the basic definition of, Cauchy's integral theorem. Cauchy's integral theorem. Now, if f of z is analytic in a simply connected domain D, then for every simple closed path C in the domain D, we have closed integral over a closed path C of f of z dz is equal to 0. So contour integral, we also call this as a contour integral. That is a contour integral okay on a simply connected domain is 0. Okay, this is a very important result. That is why we see in the previous case we did an example, we got 0. We will not go by the proofs of this. It is not required for us. There's a way by Green's theorem we can prove this. It's not required for us. Now, what are the consequences of this? So we call them as corollaries. That means because of this theorem, what is the consequence? This is very, very important, extremely important. Independence of the path. Independence of path. So if f of z is analytic on simply connected domain D, then the contour integral not just a contour integral, any integral, then integral, one thing, integral C f of z dz is path independent. All will be zeros only. Second, then integral any integral will also be path independent. Say integral between 2 points, z1 and z2, let's say, is also path independent. So first part, very easy to understand. So let's say this is C1. And this is C2. all, let's say that's all within the domain. This is C2. And let's say there is C3. It need not be a circular path. It can be any closed path. It can be C4, a triangular path. All are zeros. All are zeros. This is independence of the path for the first one. Now, for the second case, let us examine the second case. Now, let's consider 2 points. See, on a domain, let's say the whole plane is a domain simply connected. Now, let us say you have, Z2 and this is Z1. Now, I'll draw one closed path. Okay. This whole path, I'll call it as C, full path. But Z1 to Z2, I can go via this path C1, or Z1 to Z2, I can go with C2. There are two paths. The complete path is C. Now, by Cauchy's integral theorem, first by basic integration, now integral C f of z dz contour integral over C is 0, which implies integral. Now this one will be Z1 to Z2 f of z dz. Let's say I start from here anti-clockwise Z1 to Z2 and then Z2 to Z1. So I take this to the other side. Integral Z1 to Z2 f of z dz. This is using path C1. Path C2 is equal to minus integral Z2 to Z1. So now there will be a sign reversal. Now this was a closed loop, right? This was along C2. This was along C1. So this is path C1 and this is path C2. Okay. So this implies I can write integral of path C1 f of z dz is equal to integral over path C2 f of z dz. Okay. So this is, that means from Z1 to Z2, I can, it is independent of the path. So which now means there is second extension of this. This is second path. the second important corollary. This is principle of path deformation. Now, which says that, let's say there is Z1 to Z2. I need to find an integral. Now, I can use path C1. I can use path C2. I can use path C3. C4. All right. Now, based on the previous result, okay, it means that along path C1, my integral from Z1 to Z2 will be equal to integral from Z1 to Z2 along path C2. So this means that between 2 points, I can choose any path if it is a simply connected domain. So that will give me the same result. Okay. So this is Cauchy's integral theorem for a simply connected domain. Now, let us do important thing. Cauchy's integral theorem for multiply connected domain. How do we do this? The very first part is for doubly connected domain. So for a doubly connected domain, let us say so let us say this is the boundaries of a doubly connected domain. This is path C1, this is path C2. Okay. Now, according to by Cauchy's integral theorem, for closed path, all are zeros. Correct? Closed loop C1, closed loop C2, both will be equal to 0. Okay. Now, so now let us say, suppose it is not. Oh, by the way, now if it was this, suppose this is not within the domain. Now you cannot say, now if this is not within the domain, we cannot use this theorem. Okay. If it was a simply connected domain without any breaks, let us say if it is, points are not defined, then this will give you some value. Like we got 2 pi I, it will give some value. Now, let us do this. What we will do now is I will make one small cut. You see this? Very thin cut. Extremely thin cut. Here there will be a gap. I'm not showing the gap here. The gap is basically very, very thin. Very, very thin gap. Why this is happening? Sorry. I'll make a broad gap. Later I'll show that actually this is a very, very thin gap. Practically there are just two adjacent lines. The area is 0 between the two. Okay, like that. Now I will choose a path like this. Look at the, if I can put black arrows, let me see. Yeah, look very closely to the black arrows. Let me start from a point. Let's say I start here and I go this way. Then I go here, I go this way. All right, from here. And go through this whole loop, come back here. Okay. So, see my path. And I'm coming back here. And then I go through this whole loop. This entire path of with the black arrow, I call it C. So by Cauchy's integral theorem, integral on a simply connected domain okay, the integral, the closed integral is 0. Let's say this point is A, this point is B. So we get integral contour C. It's a closed loop integral. This gap, this note, path AB and path BA are two adjacent lines with negligible distance between them. So that means area is 0. So basically it's the same domain. What we have done is we have taken a path. Now I just omit. So I cover a path like this, which is a simply connected domain. Like this is a simply connected domain. There is nothing that we can tell that that this is not a simply connected domain. So what we are getting here is like this. They're not touching each other, by the way. I'm showing this as touching, but they're not touching each other. These are simply connected domains. This includes all D. It includes all D, all points D, and this contour integral will be 0. Now, I will start with this. Let us start with point A. Let A be the starting point. So this contour will be integral A to B f of z dz. Then, now this is anti-clockwise, this is clockwise. I will call it as minus C. Okay, let us C2. C2 clockwise f of z dz. Then plus integral B to A f of z dz plus integral, so A to B, then clockwise around C2, then B to A, then anti-clockwise along C1. Now, integral A to B f of z dz and integral B to A f of dz will have opposite signs and they will get cancelled. Then what we are left with, so take this to the other side. Integral C1 closed loop. Practically it is closed loop, just one point we are missing. So f of z dz is equal to minus integral closed loop C2 clockwise f of z dz. Now if I remove the minus sign, I will change C2 also to anti-clockwise. So what Cauchy's integral theorem is saying is, for a doubly connected domain, the integral over its outer boundary closed loop and integral over its inner boundary are one and the same. Okay, not just that. Okay, if you take any other path, let's say this is 0, take any other path inside the domain, again the same thing will be applicable. So that integral will also be the same. So suppose there is a region where the function is not defined or analytic. Okay, it may be just one point also, or it can be a region. Okay, here the function is not defined or analytic. Outside of this, function is analytic and it is within the domain. Now, if I choose this boundary path, or if I choose any paths around it, let's say this is C1, C2, C3, all these integrals will be equal. Okay, this is what for multiply connected domain, and it will not be equal to 0. If it was simply connected throughout, then this closed loop integral is 0. So a doubly connected domain, we have made it simply connected. Now let us look at triply connected domain. Very important result. For triply connected domain, let us choose a triply connected domain. Okay. So this is a triply connected domain. D is not defined here. D is not defined here. D is defined here. Okay. What do we do? What do we do? Again, we break. We start from a point A. Okay, maybe, and okay, let me mark the points first. And this is, let's say, it is C. This is C1. This is C2. These are the boundaries of the triply connected domain. Okay, C is the outer boundary, C1 and C2 are the inner boundaries. Now, what we do, I make a small insignificant cut here. This point is B. Okay, then A, B, and then I'll make another cut here. And let this be E, F. Now let us take with a black, I'll mark. First, let us start from A, AB. Then we go along C in the reverse direction. Then come back here. Then from BA, then we go along this path C. What are we trying to do? We are trying to cover all points D and circle along these points, these regions where the function is not defined. So we come all the way till E here, then EF, from EF we go again clockwise, and then come, I'll mark here. So then come to F, and from F to E, and again from E to A. So now this includes, see this, we are going like this, and throughout this boundary, now we have created a simply connected domain. Although it's a multiply connected domain, if we include this as the boundary, these two as the boundaries, this becomes a simply connected domain. Okay. So using two cuts, we make this into simply connected domain. Now integral over that closed loop, let the whole path be called as Z, is 0. This implies, let us start with a integral AB f of Z dz plus integral over C1 in clockwise direction f of Z dz. It becomes a closed loop. Then mark this. Then plus integral b to a f of Z dz plus integral a to e clockwise sense f of Z dz plus integral ef f of Z dz. Maybe I'll write ef down. Easy to cancel. Then plus closed loop C2 clockwise f of Z dz plus integral fe f of Z dz, then integral ea f of Z dz is equal to 0, this part. So now what happens? Let us see. This AB and BA, they cancel. Then EF and FE, they cancel. Now take these two to the other side. We get integral A to E anticlockwise. That is part 1. Plus integral E to A anticlockwise. So this is along the path, okay? A to E, E to A. So that together they form the path C is equal to minus of closed loop C1 f of Z dz minus integral closed loop C2 f of Z dz. Okay, this becomes integral closed loop C f of Z dz is equal to integral C1 anticlockwise in the same direction as that of C f of Z dz plus integral C2 f of Z dz. Very important result. Cauchys integral theorem for multiply connected domain. Now look at this. This is C and this is C1. This is C2. Okay. What it means is, suppose I'm going anti-clockwise the path C, and I have two regions where the functions and a function is not defined, and this is the boundary that defines it. This boundary. So now, whatever this integral C I have, and suppose I have 2 points or 2 regions where function is not defined, then the closed loop integrals about those 2 regions taking their sum will give me this. So if my outer circle or outer path encloses two inner boundaries, then my outer integral will be the sum of the inner integrals. Okay. So similarly, we can extend to quadruply connected domains. So let's say this path is C. Anticlockwise, and this path is C1 anticlockwise, this path is C2 anticlockwise, this path is C3 anticlockwise. Okay. Now by Cauchy's integral theorem for multiply connected domains, we get closed loop C will be equal to integral closed loop C1 plus integral closed loop C2 plus integral closed loop C3. Only condition is that they all have to be in the same direction. Anticlockwise means anticlockwise, clockwise means clockwise. Okay. Now, based on Cauchy's integral theorems, so Cauchy's, what we discussed today is simple closed path, simply connected domain, multiply connected domain. Cauchy's integral theorem over simply connected domain, a contour integral, a closed path integral is 0. And we discussed that from one point to another, the integral is path independent, and you can choose any path, you will get the same integral from one point to another. Next, for Cauchy's integral theorem for multiply connected domain, we just discussed that for a doubly connected, outer boundary and inner boundary closed loop will be equal, and anything you do in between path also will have the same integral value. For a triply connected and quadruply connected domain, the outer path integral will be sum of the inner path integrals. Next, tomorrow we'll do problems. We'll complete the last part of a very important result. Then this is very important result. The other one, conceptual questions are asked. This, so many problems are asked on this. Cauchy's integral formula. This is extremely important. Very, very important. So if f of z is analytic in a simply connected domain D, then for any point Z naught in D, if f of Z be analytic in simply connected domain D, then for any point Z naught in D and any simple closed path, any simple closed path C in D that encloses Z naught, we have integral closed loop over C f of Z by Z minus Z naught dz. Remember, now although f is analytic, but Z minus Z naught is not. It gives a point of singularity. That means function is not defined at this whole integrand, not f of Z. F of Z by Z minus Z naught is not defined at Z naught. So this value is same as this is equal to 2 pi I f of Z naught. If you remember, if f of Z is 1, then f of Z naught is 1, then we get that integral which we already evaluated. Integral dz by Z minus Z naught is 2 pi I. So this is, you can say, an extension of this. Okay. Other way of this is, or f of Z naught is equal to 1 by 2 pi I into integral f of Z by Z minus Z naught dz. So Cauchy's integral formula, one of these two. Okay. We'll not go through the proof of this. You can just remember, we can take a proof just like we did around the path e power I theta. We can take a circular path and show, and we can easily prove this. Very easily we can prove this particular result. Because Z minus Z naught, you take Z naught as the origin and take a circle. So Z minus Z naught is equal to R e power I theta. Use this and then you can get dz, okay, is dr d theta, all those things you will get. Okay, r is constant, of course, and I theta e power theta I into e power I theta d theta, like this. Using this you can prove this. We'll not get into the proof of this. Okay, so this is a very important result. Extremely important result. Tomorrow we will see the applications of this Cauchy's integral formula, and we'll show a derivative of analytic functions based on this. And then this will be used for some simple problems, a lot of problems on Cauchy's integral theorem. And its use mainly is in writing Laurent series, the series expansion of functions, complex functions in terms of, you know, z minus z naught and 1 by z minus z naught terms. So these are the few applications and problems related to that. With that, we finish complex analysis. So anyway, we have a lot of problems to do on this. So tomorrow, on Thursday's class, we will discuss this, and then again Saturday's class, we'll do problems. All right, I end here for today. Okay, I'll end the class here today. I'm stopping the recording.